that's again the best what we do. Okay, discussion section. Join us, come on in. The way it starts is that some people said, okay, we don't understand what's going on in this class. So apparently we need to start at least today we have to start over and understand what is really happening. And I hope you can see the drawings, because everything what I will be doing will be drawings on this board. Again, second question, so do you hear the microphone? Great, thank you. The class goes like that, right? So it's all about x86, which is an operating system. What we first need to understand is how the hardware works, right? And that was my biggest message was that if you understand the details of hardware, you will understand everything else. So the second thing, just an arrangement for today, and maybe in general for this class, don't be shy and interrupt me, because like I came here to essentially answer your questions, and I don't really know what the questions are. And the idea is that you have to be as vocal as possible, because I don't understand what you don't understand. That's my problem. Is that so? Don't be shy. And today is a good time to ask questions. Like even the dumbest, like even what is the register, or where is the physical memory and stuff like that, right? So I start drawing. Imagine this is memory, and imagine this is physical memory. It obviously is backed up by a real DRAM chip which you buy in a store, right? And imagine this is a CPU. As I was trying to explain in this class, everything is relatively simple. So CPU has a special register which is called instruction pointer, right? IP. Or on x86 it's called extended IP, EAP, right? What CPU is doing, it picks up instruction from physical memory and executes it, right? So be it an addition, subtraction, or something else. CPU itself has several general registers like EAX, EDX, and so on, right? And each of those are 32 bits wide, right? But the core of the computation is the following, right? So for example, if you take two registers, you can add the values which they contain and save it back into a register, right? So for example, it will be EAX equals EAX plus EDX, right? So that's relatively straightforward, right? Imagine just that's just like a piece of silicon, a bunch of transistors which do that, right? The logic of this addition. But everyone understands what's going on right here. And obviously, okay, you're done with this instruction addition. Let's increment EAP by 1, and now it will start pointing to the next instruction, right? Whatever is the next instruction, the CPU just reads it from memory, and again does something else, right? Like maybe it's a call to a function, and okay, call is a little bit hard, so let's skip it. So maybe it's another addition, right? And so on. Or maybe it's a jump. So what is a jump? Jump means that jump takes another address, right? Let's, again, for simplicity, just assume it's a physical memory. And changes EAP, right? So a jump, if this is addition, and the second instruction was jump, the target of a jump is some address, right? For example, right here. And so sure, like after this jump, the EAP will be pointing here, right? And so on. And you can imagine that, well, if you need to compute something, for example, if you want to compute, I don't know, n factorial, for example, you see how to do that, right? So you just say, well, I will be jumping in a loop n times, and every time I will be multiplying the result by n and subtracting n, roughly speaking, right? So do you understand that? Everything is very simple. That's the core. That's what happens in every machine which we have here, right? Question?
So with jump, you can always jump forward in the program. You can never jump backwards in the program.
No, you can jump anywhere, right? There is no forward and backward. It's just the address. Like, in reality, the jumps are relative. Like, go 10 instructions forward or go 10 instructions backward, because it's just shorter. Because the amount of space consumed by the instruction, like if you put a full address, you need to dedicate 32 bits or 4 bytes for the address, plus at least 1 byte for the opcode, operation code of this, saying that this is actually jump, right? So in order to make the programs shorter, they say, okay, what if we like just say 2 bytes here, so relative address, and like it's obviously like shorter, right? 16 bytes, 16 bits, pardon. Got it? But you can jump anywhere. There is no restriction on where you jump. You jump to an address because it seemed that that's more convenient than just jumping forward, right? Moreover, if you want to have loops, right? The essence of a loop is always jump backward here, right? Any question like that? Because yes, this is why we are here. So just ask those silly questions. Well, it wasn't actually silly. I apologize.
In reality, does the encrypted pointer point to like the virtual address space and then gets translated?
Yes. So the question is like, okay, I drew this picture, and immediately someone asks, okay, what happens in reality? Because in reality, it might not be physical, right? In reality, however, remember the boot lecture. The boot lecture system starts in real mode. So in the beginning of the boot, this is your reality. It has some limitations, right? Because first of all, I think machine starts in 16-bit addressing mode. So instead of 32 addresses, you can only make up 16 addresses. And obviously it was fine, but the moment you want to have physical memory which is larger than 16 bits, you need longer addresses, right? But in reality, this is totally valid initially, right? However, you're right. So I was trying to look for space, and I will probably erase here. In reality, after machine started in this mode, we immediately want to have more control of it, or over it, right? So, and you say, well, let's have a physical memory. And whatever the job says to do, address, take this value and first feed it into this something what is called segmentation, right? And segmentation will change the value of this address, right? And it will shift it, right? Because segmentation, roughly speaking, it says, okay, I have a base, some value, which is current, like let's assume, I don't want to go into the details of how base works right now, but let's assume for now there is just value base. And what happens is that base gets added to the address, right? So it's addition operation. Base plus address, so let's assume address was 55, base was 100. The address on the output here will be 155, right? And you say, well, sure, we got it. So although the address had value, I don't know, 55, in reality we're talking right now about address 155, right? That's translation from something what Intel calls logical address into linear. However, as I was saying, people say, well, that's good, but not good enough for various reasons, and majority, like, the most important is that it's not flexible, because the segmentation says, okay, you can access segments like which start at base 100 here in our example, and has some size or limit, right? And like address 55 is right here, right? You get the point, right? Because we added 100. but what happens is that people would say, okay, we want to control memory at the granularity of smaller chunks. And those smaller chunks are called pages, right? They are 4 kilobytes in size. And in order to use pages, what happens is that the hardware takes the result of this segmentation translation and feeds it into something what is called page tables, right? And I will explain in a second how the page tables work one more time, but let's assume that it takes something as an input, something what is like, we call it linear, and outputs physical address. And so page tables can change the address in any possible way. Okay, let me erase this one so I have more space here. Specifically, what can be done is that it can map to any region of physical memory, right? Without any specific offset. So by changing the translation, you can remap addresses. By changing the values in the page tables, you can remap the actual physical addresses which match a specific linear address, right? Okay, at a high level, again, is that clear, right? Or are there any questions which are?
Question?
Yeah.
What is the difference between a logical and a virtual address?
Okay, logical the way it goes is that something what you have in the register, like when you did this jump, or like as an argument to an instruction, it's called logical. This logical address consists of 2 parts, the actual offset, and the second part is something what is in your segment register, right? So in this example, since this is a control instruction, we're talking about control CS register, control segment register, right? So this is called logical, consists of 2 parts because it doesn't exist as a single part. Neither CS or offset alone do not define an address, right? But imagine they together create an input to the segmentation unit, and it outputs something what is called linear address. This linear address, I mean, it doesn't really exist anywhere physically, but exists somewhere inside the CPU, right, at an intermediate result. And if the page tables aren't, if the paging is not enabled, linear immediately becomes physical, right? And it goes to the actual physical memory controller saying, okay, give me the data which is at this physical address, right? Like, imagine a memory controller as something like you have a CPU and there is some kind of a bus which connects you to memory, and this is the address, the physical address, which essentially controls what you read. So some address from here, right? Some value from an address, at a specific physical address from the actual DRAM chip, right? You got the point, right? But normally, in most of the systems which we see today, right, people say, but by the way, we want to use page tables. And the linear becomes input to the page tables. And the page tables somehow, according to some rules of this address, right, and specifically remember this is my like favorite 10, 10, and 12. Okay, didn't come out as clean as I expected, but essentially you choose an entry here, and get a physical address as an output. And as this physical address goes to the memory controller, right? But conceptually, it's not that hard. So logical consists of 2 parts, goes through segmentation, becomes linear, linear goes through page tables, becomes physical, right?
What is the CS that comes from logic?
What is this error which comes from
Just what is the CS stand for?
CS, control segment register. Okay, let me explain now how segmentation works, right? So people remember that the way it works is, and again, it's a little bit archaic because no one really uses it. Okay, just let me make it clear right now. Well, the segmentation is there, and the hardware for segmentation is there. In reality, do you remember, like 2 minutes ago, I was mentioning base, right? In reality, on most modern hardware, on most modern operating systems, the base is always 0, and the limit or size of the segment is always 4 GB, right? And Intel went even further and said that on 64-bit machines, you can't even change the base or the limit. They always stays the same, which created like a range of complications for people who build operating systems. But again, like it's probably not the main point of today's lecture. So today we can just say, okay, sure, in x86 the base is always 0, the limit is always 4 GB. That's why this translation like doesn't change this offset. So this linear errors will be the same, like it will be the same offset, right, with no changes at all. That's why like you can call this one virtual, or you can call like this address virtual as well. Essentially anything before the page tables you can call virtual if you like. And it's normal, just make sure that you know the assumption that these guys are disabled, essentially. Disabled by the fact that the base is 0, doesn't change the offset, and the limit is 4 GB, doesn't limit you to anything. Right? So is that clear? Okay, so do you want to hear how the segmentation works? Or, because my kind of high-level goal today was to, this is a bunch of low-level details, but the high-level picture is a little bit different, and maybe it's more important to understand the high-level picture. So let's assume just for now that we know that addresses gets translated somehow. So, and we know that addresses from the, like, when they exist in the, as arguments to instructions like jumps or reads from memory, got somehow changed, right? What I wanted to explain you, again, my wonderful, most important figure here is that if you have physical memory, essentially what you have is like physical memory and the CPU, which runs programs, right? So it executes instructions by instructions. And you can imagine, okay, I got it. So I kind of believe that I understand how you can compute n factorial, but I totally don't understand how you can see multiple windows on the screen, right? Or send email or stuff like that, right? So, okay, I don't know, that's your screen kind of, I guess. So, and this jump seems to be a little bit counterintuitive because like this is a totally flat figure. You say, you start here, you move forward, you may jump somewhere, you move forward again. But still, it's not clear how you get windows on the screen, right? So that's what we want to understand. And I mean, that's just the whole point of this class is to explain it. And remember that the way everything starts is from this bootloader, right? So the BIOS essentially says, okay, some other part which was running on the system before the operating system says, okay, I will load this piece of code from disk in memory of the machine, and we'll jump here, right? And after that, everything starts, but everything just flat. But what happens is that this first part loads more code from disk, right? Something what we call a kernel. But the kernel is nothing different from the original bootloader. It's just some machine code which is compiled by like a combination of a C compiler like GCC plus assembler and the set of tools is always the same. Compiler, assembler, linker. If you, like in a high-level language, you never touch the machine code, so you don't need assembler, but linker still stays normal. And again, what's important here that you end here, you jump somewhere here, you start jumping back and forth. And if you want to remember where you jumped from, right, if you want to come back, you do the following. You say, well, instead of jumps, I will use something what is called call, right? So it's yet another important instruction on the CPU, which is very similar to a jump. You say call and address, or often calls are also relative addresses. But instead of just simply, if your EAP was here, instruction pointer was here, that's your call instruction, and you're jumping somewhere here, for example, before jumping, or at the moment of jumping, one part of this memory is designated as a stack, right? So, and it's pointed by yet another hardware register, which is called stack pointer, SP, or Intel calls it ESP, right? And what happens is that the call just says, okay, I know that you want to execute a subroutine, like a function, and I know that you want to come back. So I know that you want to continue at the instruction which is right after the call instruction, right? So it saves it. It saves this value, I don't know, A. Okay, let's say address 2 on the stack here. So if instruction pointer is pointing here, okay, let's make it grow downwards like normal. This is the same memory. It points straight here, and this is where you will save this error. Address 2, right? So that's the role of the stack, which means that you remember, it's kind of like a note on a table saying, okay, if I forget to make a sandwich tomorrow, here's a note. I was about to make a sandwich, but decided to go to bed, right? And you come back, say, okay, sandwich, and you make a sandwich, right? So you just remember what you want to do next. You got the point, right? And obviously, well, you can return, this gets erased and stuff, but it's the same kind of model. You still keep jumping back, right? So, but it's more powerful jumping. On top of this, you can obviously build like a regular language, right? So you can build something like C. You have main, you have functions here, foo, you jump inside foo, you come back from foo, start executing bar, and so on, right? But originally, this thing still just executes here. Nothing changes. Same bootloader or here in the kernel, right? Now the question is like, what about those windows? Because the window is an abstraction, meaning that you say, I want to run multiple processes, right? I want to say I have window for process 1, P1, or application 1, if you don't like the word process, and P2, right? So conceptually, how you can achieve it? You say, well, if I have a region of memory here dedicated for example, P1, and a second region of memory dedicated for P2, you kind of say, well, I kind of got it. So if I want to run a little bit of P1, and I know that the main entry point is here, main, why not to just, like, at some point, jump to this entry point and continue executing here, right? You will be executing, CPU does the same, because it doesn't know that you meant to jump to a different process or anything like that. It will start executing here instruction by instruction, right? At some point, maybe this process is a good guy and decides to say, well, I'm kind of done, and invokes a yield function saying that I want to jump back to the main control application, which I will be calling kernel. And so you jump from after like yield is here, right? Or a call to yield. Call yield. And which means that you're jumping back here and start executing in this region again. And then maybe you say, like, you can imagine that you can maintain a linked list of these processes, right inside here, saying I know that P1 is process 1, P2 is process 2. So P1 ran for a little bit. Why not to jump to P2? P2 starts here, for example. That's his main. And obviously, after this, you just jump to main of P2 and start executing P2, right? But again, you're just jumping between them at a high level, right? So how do you arrive to this figure of having something on a screen? What happens is that, imagine there is a piece of hardware which is called a screen, like LCD screen, for example. And it also, like, the hardware people said, okay, if you start writing into this region of memory, which is called frame buffer, for example, some values, we will show them as pixels on the screen, right? So at this point, you kind of say, well, I got it. So I will designate yet another process, which is, I will draw it here at the bottom because I ran out of space on the top, but it's the same process as P1 and P2. I will call it P3, but I also will call it something like a window manager. And the goal of this window manager, and I apologize for this handwriting because chalk is very convenient. The window manager is yet the same instructions, but what they do, they somehow collect information from individual programs about their individual frame buffers, like, I don't know, like numbers here, right? Or letters, and maybe whatever, maybe it's a drawing here. And composes them in a single frame buffer by computing like which window is on top of which one, and essentially if here, like the text is on top of a flower, it will compose as text and a flower in the background, right? And the hardware itself picks it up from here and essentially makes a bunch of pixels on an actual physical device which you can see with your eyes, right? Okay, do you think you understood this? Like essentially we only have like 4 things, like, or maybe 5 including the bootloader. Bootloader starts the kernel, kernel starts 2 processes, P1 and P2. They all have designated regions of memory. When I say designated region of memory, it's just like, I don't know, it's just a data structure like a buffer, char, I don't know, some size, something like, I don't know, some 4 kilobytes, for example, for representing the data on the screen, right? And then the one process composes everything together and essentially, like, again, prints it or moves it, like, copies into a region from which the hardware can pick it up and show it on an actual region, right? Okay, is that clear? Or like, it's time for those questions, like where you say, okay, I don't get it, so. Yes, no? Go ahead. Yeah.
For processes to run like concurrently, do you have to use stuff like fork? Is that where it comes in? Or
What is fork? It's a good question. What do you think? Okay, good story. Where is fork here? How can you implement fork?
in the kernel?
In a kernel, right? So here there will be some code which will be forked, right? It's just a function. At a high level, it's just a function, which at any point of time, instead of calling yield, you can call fork. And the result of this function is that you obviously jump here, and this part of the code says, okay, I will copy your memory somewhere else. And remember memory allocator, so it finds unallocated region of memory, physical memory for now, and says, okay, that will be, I will just copy you here. And you have identical copy, and obviously you add it to the list saying that it's now P whatever, P4, and you continue, you jump between them, back and forth, right? That seems to work. And one of them might be computing factorials, one of them will be whatever, maybe your email client, right? What else? That's a good question. Where is fork? Like questions that are important. So ask another one like that.
How is global descriptor table used for this?
Okay, good question. Remember my story about the fact that we translate addresses, right? One simple thing is to say, well, in this example, each of these processes starts at its own physical address, right? So one starts at P1 or whatever, address AP1, address of process 1, or physical address 1. Another starts at P physical address 2, right? It's kind of cumbersome because you can't, when you do the fork and you do a copy, you have to change all the addresses in this process to make sure that they start at something what is like here, PA4, right? What you can do instead is to say, well, I will use something what is called segmentation, which what we just described, and say that before jumping, instead of simply jumping to this new process, right, you will change the value of a couple of registers, specifically code segment and data segment registers. And those registers will be pointing at the table, which is called global descriptor table. The table itself is also somewhere in memory, somewhere here, right? But what the hardware will be doing is, if CS, for example, contains value 1, like in this example, this is entry 0, but this is entry 1, and inside this entry 1, there will be like two important values. One is base, and one is limit. And so the base will be participating in the translation. So for example, for this process, if you have an address A, the physical address which the hardware will send to the memory controller will be what? A plus base, right, exactly. Do you think you understand? I forgot, you asked the question, right? So did you get it? And now before jumping to process 2, you say, well, I will change CS to point to entry maybe like somewhere here. And this is how it was done, let's say 30 years ago, before the page tables were mainstream in hardware. Or like they were not, I believe they existed, but they were not deployed. But today we say, okay, this model is fine. But for example, again, a simple example why you would like to have something more sophisticated than segmentation is, imagine you say, well, this region of memory of this process never gets used, but it occupies space here, right, in physical memory. And you say, what if I want to run another process? And it seems that, first of all, I have kind of like a couple of those gaps, the regions which are not yet used, but they are, first of all, spread all over the physical memory, and second of all, this one is still used. I kind of just know that it's idle, and most of the time it's not used, right? But, so why not to copy it to disk, for example, right? And that leads you to this fine-grained, the idea of managing memory at finer granularity, finer than just segments, right? And this is how we arrive to the idea of page tables. And page tables, at a high level, implement a very simple idea. The idea which is the following. Imagine you have physical memory. And imagine you have address spaces of process 1, P1, and address space of process P2. And instead of if segments would allow you to align them in the physical memory like that, right? That's what segments can do. Obviously, they can overlap. The page tables would allow you the following picture. The page tables say, okay, let me quickly erase here. Just checking that the recording is on. So the page table says, okay, by the way, I can map I can choose any physical page to be in this address space by adding it to the page table, right? And so, and by the way, not all the address space have to be actually in physical memory. So maybe I just want to have two pages, two physical pages, 1 and 2, to represent these two virtual addresses, to represent these two virtual pages, V1 and V2, right? And maybe, why is it useful? Because maybe the code in this program just jumps back and forth between these two regions, and everything else, like this page is not even touched ever, right? There is no reason to waste a physical page of memory for these addresses, right? So you can align them like anywhere, choose them anywhere in physical memory, and let the CPU jump between them, right? For as long as you want. And so, but you got the point, right? It was the page tables. And in this picture, you say, well, since the page tables are so powerful, there is no reason to say that I even need to do anything with segments. So you can say the base of this process is always 0, and the base of this process is always 0, right? So any address which starts, like, let's assume this is address which starts at address 10, will supposedly go right here, but since it goes to the page table, we take this 10, split in 10, 10, and 12 bits, use the two levels of page tables, and the top 10 bits choose an entry in the first level, the middle 10 bits choose an entry. If you have a pointer to here, it will, these 10 bits will choose an entry right here. And this will contain a physical address, right? And the last 12 bits will choose, if the physical address chooses a page itself, the last 12 bits will choose an offset within that page, right? Is that clear?
Wait, so why again wouldn't there be collision if both processes start with a base of 0?
Because you take these guys, let's assume same address 10, for example, right?
Yeah.
But it goes into another page table because each process will have its own page table. And yes, it chooses the exactly same entry here. However, the page table itself, if this is the page table of one guy, and let's assume it's located, this page itself is here, and this one is somewhere here, right? For this guy, it will be somewhere else in physical memory, and those values will be different in physical memory. And so you will, again, you will choose this page, the value will be different, right? The value of physical page which chooses the, which stores the second level of page tables will be different. It will choose this one. And this actual physical address, which is contained here, will map us to some other page, right? And that's why there are no collision, right? It's like, those are just tables at a high level, and you can configure them to point to any physical pages, right? So, okay, this is kind of interesting, okay, but there is a question, go ahead.
So to access the page table, there's a register to have the address of the page table, right?
Can you ask again? I missed what you said.
So for the page table, there's a special register that stores the address.
Right, yeah. There is a special register which is called CR3, control register 3. I mean, I apologize for cryptic names. I just keep using the names which Intel is using. And the CR3 contains a physical address of this page, the root of the page table, which is currently used by hardware, right? And every time, remember those jumps between processes. Every time you jump between processes, you will change the CR3 to point to the page table of a different process when you jump to a new one. And this is where system calls are important, because when you exit into the kernel, you stay on the same page table, but then you essentially load a different one and jump into another address space. And these things are called address spaces. And the address space is represented by a page table. If there is a page in an address space, there will be an entry in the page table. If there is no page, the entry in the page table will be just invalid or not marked as present.
So if segmentation is not even used, why do we need it to have page entries?
For backward compatibility reasons. I believe the original reason is backward compatibility, in reality, people today, as I was saying, are very eager to use segmentation for security purposes. But essentially, like, imagine, okay, I don't want to get into those details, but yes, today there is a need. There was a gap of time where people decided, okay, like you said, why do we even need it? That's why on 64-bit hardware, Intel said, okay, since no one needs it, let's just remove it, right? There's one important role of segmentation, right? So who can tell me which one? Oh, yeah, segments and segmentation, which is still used today. Remember, segments encode privilege levels. So, and privilege levels are part of the isolation and security model on Intel hardware. Remember that processes run at privilege level 3, and the kernel itself runs at privilege level. And you have your discussion section here.
We have a class right now at 6 o'clock.
Sorry. Okay, yeah, we're getting out of it here. Okay, sorry, I didn't realize that there would be another class. But, okay, so tell me on Piazza again, if you want another session, we can do that. If this is good enough to start understanding what's going on.